In order to find the heat loss in a steam cleaning water hose, I looked at the internal convection of the water and energy balance. In carpet cleaning, besides the chemicals to break down dirt and grime, heat plays a big role in the cleaning process. It's important to be at the correct temperature. Too cold, and the dirt won't lift out very well. Too hot, and it could damage or even melt the carpet. I wanted to see how the different lengths of hoses affect the amount of heat loss as the water flows through the hose. One evident way that shows this is the temperature difference between inlet and outlet. The method of measuring the water temperature is very simple. A thermocouple is fastened to the end of a shorter hose so that the exiting water contacts the thermocouple just as it leaves the hose, as shown on the left. In the center, the short hose is attached directly to the truck-mounted engine. The end of this hose was recorded as 0 feet, and set lengths of 50 and 100 feet hose were added, and the outlet temperatures were measured for each of the additional lengths of hose. The image on the right shows the inlet hose temperature of 95.7 degrees Celsius. Now that we have the inlet temperature and outlet temperatures for hose lengths of 100 feet, 150, 200, and 300 feet, which are recorded on the left along with the inlet temperature at 0 feet of hose, they are converted to Kelvin. Because of the small internal diameter of the hose, about 1/4 of an inch, we can accept that the measured temperature from the thermocouple is the mean temperature, TMI or TMO for inlet and outlet temperatures. Now, assuming that the only mode of heat transfer is convection, we can use an energy balance and the equation for global internal convection. We see that Q equals m dot Cp times TMO minus TMI. Using the density, velocity, and cross-sectional area to find the mass flow rate, the first equation becomes rho VA Cp times mean outlet temperature minus mean inlet temperature. The remaining unknowns then are the density, velocity, cross-sectional area, and specific heat. To find the velocity, I used projectile motion and kinematic equations with a known height and distance seen in this picture where the end of the hose was up by the stairs and aimed in the direction of the blue arrow. It was easy to find where the trajectory landed because it left a bunch of patches of dead grass. With the height y of 3 feet, gravity, and horizontal distance x of 7.5 feet, the time of trajectory and sequentially the velocity was found. The cross-sectional area is found using the measured internal diameter of about 1/4 of an inch. The only other unknowns to find the heat transfer are the density, which is 1 over specific volume, specific heat, and any other values if needed. Those can be interpolated from the tables, given the outlet temperatures. Now we can find our heat loss of the water as the length of the hose increases. Calculating all of the Q values at hose lengths of 100 feet, 150, 200, and 300 feet, this shows that as the length of the hose increases, the energy loss due to heat transfer, Q, also increases. The values of the heat transfer starting at 100 feet and increasing are 2.14 watts, 3.27, 4.37, and 6.12 watts. While examining the graph, it's quite linear. It has an average heat loss of about 1.32 watts for every 50 feet of hose added. I feel it's important to note that as the overall hose length increased by 50 feet, the outlet temperature decreased by about 3 degrees Celsius, shown at the left, which shows a linear trend as well. When compared to the basic mode of heat transfer of convection we learned in Chapter 1, Q equals HA delta T, it was found that there was a consistent upward linear trend as well, seen in red, but with an offset of about 20% error. I believe that this was because there are a few assumptions that were implemented. First, the temperature of the surface where the water was in contact with the hose could not be measured, as the hose is an insulated hose. Thus, I assume that the change in temperature, delta T, was the same change between the mean in and mean out temperatures used for internal convection. I neglected any other modes of heat transfer and also any convection that might have taken place from the water to the insulated lining of the hose. With that being said, being able to measure the inner surface temperature of the insulation and including the insulation itself in the analysis may yield better results. Additional analysis regarding these carpet cleaning hoses would be to see how different surfaces that it lays on affect the heat transfer and exit temperature. For instance, if the 100-foot of hose is laying on concrete versus grass, or dry carpet versus wet carpet. Looking at the results, we see that as the length of the hose increases, the heat loss increases by about 1 to 1.5 watts every 50 feet of hose, and the exit water temperature decreases about 3 degrees Celsius every 50 feet of hose as well.